Okay, class, we're going to talk about collision theory and something called activation energy. And we're going to see how this relates to rates of reactions. All right, so let's just reveal this whole entire slide. We've talked in the past about collisions between molecules when we talked about gas laws, and we talked about kinetic molecular theory, and the word kinetic is in that, and we're going to see how these collisions are going to relate to reaction kinetics. So, and we're going to look at these collisions in a way of thinking about how these collisions might affect reaction rate. So applying collision theory to the rates of reaction. Well, let's kind of look at some of the factors that might affect reaction rate. Well, concentration. Been there, done that. We've talked about that. That if you have a greater concentration of particles, then those particles are going to collide. They can only react if they collide with one another, because the two molecules have to be close enough to one another to exchange bonds. And so that comes from the collision. And so the higher the concentration, the faster the rate, because there's more collisions. Temperature. Temperature is going to cause molecules to move faster. If they're moving faster, they're going to collide with more energy, and they're going to collide more often. And that's kind of all relates to the frequency of collisions, and so the orientation of the molecules when they collide. And we're going to talk more about that on a separate slide, but these are some of the factors that kind of come in when you look at collisions versus reaction rate. And then finally, when molecules collide, there's a certain energy of that collision, and it's going to turn out there is a minimum energy that the collision has to have in order to get the reaction to happen. This minimum energy is called the activation energy, and it has the symbol E sub A. And so for the rest of these notes, we're going to be looking at these factors: concentration, temperature, frequency of collisions, the orientation of the molecules, and this thing called activation energy. And we're going to apply that to reaction rates and see how they would affect them. All right, temperature and rate. We've talked about this before. In general, as the temperature increases, the rate will increase. But it increases, if you think about it, it's increasing the rate. I mean, let's say if the rate is this, the rate is, K times the concentration of something to some X, right, to the power of its order. Temperature doesn't appear in that equation. Temperature doesn't appear in the integrated rate law equation. So how will temperature increase rate? The temperature increases the rate by affecting the value of K. It turns out that the value of K is temperature dependent, and it increases as temperature increases. And if I think you recall, I said there was sort of a general rule, kind of a rule of thumb that says for every 10-degree rise, a Celsius rise in temperature, the value of this rate constant will double. Again, it's not, this is just a rule of thumb. Sometimes it triples, sometimes it quadruples, sometimes the value of the rate constant only goes up by 1.5, but it will go up as temperature goes up. So again, this collision model of chemical reactions is based on kinetic molecular theory and the idea that molecules are constantly in rapid, random motion. And it also says that molecules must collide in order to react. Again, like I mentioned before, if two molecules for example, you have A that's going to collide with BC. If they are as far apart as they are before the collision, how are they ever going to react? So they must come together if they are going to react. And you see here then what happens is, A will collide with BC, and then the energy of this collision will provide the energy, in a sense, to break the bond between B and C, and then allow A to bond with B, and C would go off separately. And so then again, if there are more collisions, right, then more reactions can occur, and this is why we say that increasing the concentration will increase the rate in general. Of course, we know there's zero order where the concentration is independent, or the rate is independent of concentration. But in general, the more the collisions, the more the reactions can occur. Let's look at orientation. That was another factor that came into play in the collision model. That what you might think is that most of these collisions that are happening will result in a chemical reaction, and that is not true because there's a couple other factors besides just concentration and the collision itself. First, there's the orientation of the molecule. So as we said, molecules often collide and they don't form product. They just bounce off one another. It turns out that when the molecules collide, they have to collide in a specific alignment, all right? And if they're not aligned properly when they collide, the breaking and reforming of bonds won't happen. Let's look at the example in the graphic down below. You have a molecule, a single chlorine kind of molecule or atom, colliding with whatever this is. It looks like it's a chlorine bonded to a nitrogen and an oxygen. Okay, so whatever, NOCl, let's say, whatever that species is. And when they collide, you're going to make chlorine the element, and then you're going to make NO. But if you think about it, this collision might result in a reaction because you're making Cl2, and the lone chlorine is colliding with the chlorine end of the NOCl. And then that way, this collision can cause the chlorines to bond together and then the nitrogen monoxide to go off. But what if we look at the lower graphic where the chlorine is colliding with the oxygen end of NOCl? Well, the chlorine and oxygen aren't part of the reaction. You're not making ClO, you're making Cl2. So you can see the orientation is important because if the chlorine collides with the oxygen end, or envision the chlorine colliding with the nitrogen part of NOCl, it's not going to react. They'll just bounce off one another. So the orientation of the collision is important. So you need collisions, and then they need to be oriented properly. Also, there is again a minimum energy needed for a reaction to take place. This minimum energy that the molecules need before they can react is called the activation energy. Oops, sorry, it always does this. The activation energy, okay? And again, it's the symbol E sub A. E sub A is an energy barrier that must be overcome in order for the reaction to take place. But where does this energy come from? The energy comes from the energy of the collision, okay? So if you have like in the example of A colliding with BC, we had that example on the previous slide. If they collide, but they collide with a very low energy collision, that energy of that collision will not be enough to, in a sense, allow the bond between B and C to break so that A could bond to B. But if it collides with a forceful collision, a more forceful collision, a more energetic collision, then that provides the energy, this barrier to this reaction. If they don't collide with this certain minimum amount of energy, they're not going to be able to react. But if they collide with greater than that energy, greater than that activation energy, then they are able to react. So you can kind of see the fun graphic over here is of the frogs. Whoops, sorry. And the frogs are trying to jump over. They're trying to get to this other pond, but there's a barrier in their way. And in this case, that's the activation energy. So this would be like the reactants. They're trying to jump over the barrier. If they are able to jump, if they get enough energy, they can jump over and get into the other pond. But if they don't, then they'll hit the wall and they'll stay reactant. Look at the graph. That's sort of a fun way. Let's look at the graphic below. Well, this reactant has a certain potential energy, all right? And it collides with a neighbor, and that provides enough energy. And this is the potential energy scale. You can see the molecule then, in a sense, rises up on the potential energy scale, all right? And then it turns out that this amount of energy here, notice it's labeled EA, if these molecules collide with this much energy, then they raise their energy to this point at the top of this hump. And then that is the energy that allows these bonds to break and reform to make the product. This is a different product than the reactant. So this minimum amount of energy of the collision is called the activation energy. And at the point at the top of this slide, at the top of this hump, is called the complex, or this high energy collided molecule is called the activated complex, or the transition state, because it's at this high energy state, this higher potential energy state, that the reaction is going to transition from reactant to product. So let's look a little bit how temperature might affect this activation energy barrier. Okay, in this graphic, we're going to look at our Maxwell-Boltzmann distribution. Again, we're talking about kinetic molecular theory, all right? And that in kinetic molecular theory, when we talked about gases, we looked at the Boltzmann distribution. The x-axis is kinetic energy, right? The energy from the motion of these molecules. And again, the y-axis is the fraction or the proportion or the percent of the molecules that have that kinetic energy. You recall that we'll just look at the blue and the red humps here, graphs here, and then we'll look at the text on this page in a second. We know that at a lower temperature, there's a lower distribution of kinetic energies, and at a higher temperature, right, it shifts to the right, and the distribution spreads out, right? That's your typical Maxwell-Boltzmann distribution. Well, what would this have to do with temperature affecting the reaction rate? Well, if you look on this graph, there is a vertical line here, and this is on this kinetic energy axis. There's this minimum energy, right? This activation energy. This is the energy of the collision, right? And it's marked on the energy scale down here at this point right here. So however many kilojoules that is, when these molecules, either at a lower or higher temperature, collide and they're going to react, they have to collide with that minimum amount of energy. Let's look at the lower temperature molecules first. Well, if you look, what percent or what proportion of these lower temperature molecules will have enough energy, have higher than the kinetic energy, that they're going to collide with that minimum energy, right? There's a very small proportion right here. But if we raise the temperature, and the distribution skews to the right, you see that there is a greater proportion of molecules then that have the kinetic energy that is greater than this minimum energy. So the molecules that collide out here will collide with enough energy. So you raise the temperature, and there's a larger fraction of molecules that will collide with the activation energy minimum. So to summarize kind of what we talked about on these three slides, first of all, for a reaction to occur, according to collision theory, there must be a collision. Okay, you have to have a collision. The collisions must be in the proper orientation. And the energy of those collisions must be greater than this minimum energy that's required for the reaction to happen, this activation energy. And so what in a sense, you can see that in most cases, only a small percent of collisions will result in a reaction. Because again, first you have to collide. Okay, yeah, there's a collision. But if it's not in the proper orientation and it's not a collision with a certain amount of energy, a reaction is not going to happen. Okay, now what's going to put all this together? Well, it turns out our old friend Arrhenius, who we know from acid-base fame, also studied reaction kinetics. And he found a relationship between some of these variables and how these variables numerically will affect the value of K. So not just saying, oh yeah, if the temperature goes up, K is going to be larger. Or if you have more collisions, you're going to have a faster reaction rate, right? Or if you have more energetic collisions, you're providing the EA that will allow the reaction to occur. No, that you can actually mathematically relate some of these variables. And so this is the rate, right? This is your typical, rate law. Again, this always does this. This is your typical differential rate law. And again, temperature and all these things do not appear in this equation, but K does. And so what Arrhenius found was that the value of K was affected by the temperature and the activation energy, and a third factor called the frequency factor. Okay, and this is the relationship he found. Interestingly enough, you have a natural log, or you have, E, which is the base of the natural log. And the other thing that's interesting is, even though these aren't necessarily gases, right, because liquids and solids and aqueous things can also collide, the gas law constant appears in this. And so there's a case, and I think I mentioned way back, that when we talked about gas laws that are what you call the universal gas law constant, or the gas law constant, works, applies to the ideal gas law, but it also applies in other places in chemistry that you might not think it should apply. So it's sort of this value, this quantity that appears in many places in chemistry, and we're going to see it's going to come back again when we talk about chemical equilibrium and when we talk about thermodynamics. It's just kind of this crazy constant. Anyway, back to the Arrhenius equation. What Arrhenius found was that the value for K, right, is equal to this thing called the frequency factor. So it takes into account the frequency of collisions, like, and that would be given a number, and this would be, Z would be what percent of molecules are colliding with one another at any one time. And then something called the orientation factor, which would be a sort of a fraction or a percent of what percent of collisions are in the right orientation. Okay, so this factor includes both of those. Then you have your gas law constant, like I mentioned, and we're going to use the value of the gas law constant, 8.314 kilojoules per mole degree Kelvin. So instead of liter atmospheres per mole degree Kelvin or liter kPa per mole degree Kelvin, we're using it in this form. And then EA, again, is the activation energy. And so you can kind of see, how would then temperature or activation energy or the collision factor, the frequency of collision, and the orientation factor, how would those affect the rate of the reaction by affecting the value of K? Well, one good thing is, the College Board is not going to ask you, and I'm not going to ask you, to actually calculate anything here with the Arrhenius equation. I'm not going to ask you to calculate anything with the Arrhenius equation. What the College Board and myself want you to know about the Arrhenius equation is, can you just look at the equation without plugging in numbers and then conceptually talk about how the value of K would be affected? So let's go through a few of these. So if temperature increases, using the Arrhenius equation, you would see, temperature is in the denominator of this exponent, okay? And so if temperature is larger, right, then the negative exponent gets smaller, which means that e to that negative exponent will be a larger number. So then you'll have K is A times some larger number, and so K will increase. If temperature decreases, then this exponent, EA over RT, will become a larger negative number. E raised to that larger negative number will be a smaller number times A. K will decrease. So you just kind of have to work through, what if the T plugged in was larger or smaller, and then how would that affect the value of K? What if the activation energy is large? What if this reaction requires a huge energy collision, a high energy collision, okay? That would mean it has a high activation energy. So that would mean that this EA here would be larger, okay? EA would be larger. That would make this a larger negative exponent, correct? Would make it, right? If this is larger, it'll be a larger negative exponent. So e to that larger negative number would be a smaller number. So K would decrease. So if you have a high activation energy, the value for K is lower. If you have a low activation energy or it's smaller, again, then you have a smaller number here in for EA. This exponent gets less negative, so e to that less negative exponent is a larger number times A. K will increase. All right, lastly, what if the number of collisions increases? That's your concentration effect right there. Well, because this A factor includes the frequency of collisions and that orientation factor within it, okay? If the collisions increase, well, then the value for A increases, so K increases. So this is how concentration, having a higher concentration, may increase the rate of reaction. Finally, if there's something you can do to the reaction to make the orientation factor improved, for example, if you can do something to the reaction to allow a higher percent of collisions to be in the proper orientation for reaction, then the A factor will increase and therefore K will increase. And I'm going to give you a little hint. It turns out that some catalysts act by improving the orientation factor. Ooh, baby. Now, lastly, this is one little extra fun fact about the Arrhenius equation. It's beyond the scope of AP Chem, but if you rearrange the Arrhenius equation, okay, where you take the, e to the negative EA over RT factor, okay, out, if you kind of rearrange it a little bit, okay, where you basically take the logarithm of both sides, okay, you find this equation, right? So if you take that, K equals A times e to the negative EA over RT, and you take the natural log of both sides, this equation results. Well, now if you see this, then this is a straight line equation where the ln K is a Y, negative EA over R would be like your slope, and then temperature, or 1 over temperature, because this is 1 over temperature, is like your X, and then the y-intercept will be your collision factor, or your frequency factor. You kind of look at this, and you can plot, if you can run this reaction at different temperatures, okay, and this is 1 over T. I realize it's hard to see the x-axis scale here, but the x-axis is 1 over T. If you can run this reaction at least 2 temperatures, right, and it's a line, and you find the slope of this line, this is really cool. If you find the slope of this line where you plot the log of K, right, versus inverse of T, the slope of this line is the activation energy, negative activation energy, over R. And so the slope of this line can be used to find the activation energy for this reaction. You may wonder, how do we know the activation energy for certain reactions? Well, you can find it, and all you have to do, this is a difficult experiment to run, but because you'd have to find the value of K, but you just have to run a reaction at 2 different temperatures, find the value of K at those 2 different temperatures, and then plot the natural log of K versus 1 over T. Again, the slope of that graph can be used to find the value for the activation energy. And the other thing is, you may wonder, how do they know what the frequency factor is? How do they know what the value for A is? Well, the y-intercept here is going to be the natural log of the A factor. And so using the Arrhenius equation and some, pretty sophisticated chemistry, you can find these things out. You can find the value for the activation energy, and you can find the value for the frequency factor. So very, very cool. Although, again, this is just a little added knowledge on your end that this is how these quantities can be found. But we're never going to have to do this actually in class. Now, finally, we're going to move on to a different topic, called reaction energy profiles. I believe it's 5.6. Anyway, these are graphs that you've probably seen before. In fact, there was a graph like this on the slide with the frogs on it, right? So what is a reaction energy profile? Well, this graph right here, oh darn it, I do that all the time. This graph right here is a reaction energy profile. Well, what does it show? Well, there is the x-axis is what we call reaction progress. So this is the reaction proceeding, I guess, through time, right? It's not really time, but you'd say that initially, though, you can see that there's only reactants. At some point, then, as the reaction progresses, you have reached that activated complex, that high energy state that is reached by a collision that has the minimum activation energy. And then we can proceed, we can progress on to products. The y-axis is potential energy. You've seen these graphs before with potential energy versus some x-axis. So let's look at a couple of different ways this can look. Okay, so in the left-hand graph, we'll clean this up a bit, right? The reactants start out at a fairly high potential energy. It's okay, that's not bad, okay. And then they collide, and then it turns out that this reaction does not have a very large activation energy, right? It has a very kind of a small activation energy. In other words, these particles here don't have to collide with that much energy in order to reach this, what we call activated complex, okay, where they're going to be able to react. And we're going to look more at this activated complex state over the next couple of classes. But, well, then they can proceed to products. And we see that these products, the bonds, so this, in a sense, this line right here represents the energy of the bonds of the reactants. This line down here, or this value here, represents the energy in the bonds of the products. And you can see, and then again, we have the middle one is the energy of the activated state, this height up here, okay? And this difference between the reactant energy and the peak is the activation energy. Anyway, and that goes down. But if you look at just the difference between the energy in the reactants and the energy level of the energy in the bonds of the products, and you find that difference, it is called delta H. In a sense, this is the energy change, the overall energy change. Remember, delta means change. Energy change of this reaction. You can see that the energy goes from a high level to a low level, but we know energy has to be conserved. So where does all this energy go, right? Where does all the energy go that is the difference between the reactant energy and the product energy? Well, this is then sent out as heat. And if you remember, I'm sure you did some thermochemistry in honors chemistry, and so you should, this should not be unfamiliar with you, right? If the product energy is lower than the reactant energy, but energy has to be conserved, where does that energy go? When you go from reactant to product, it is converted into heat and sent out. Okay, let's look at the right-hand graph, okay? Well, you have your reactants down here. They have a lower potential energy. These particular reactants in this reaction have to collide with a large amount of energy before they can reach the activated complex. So they have to collide, they're coming together, but if they don't have a very large energy collision, a very high energy collision, they're not going to reach the peak. If they have a low energy collision, they might move to here on the energy scale, and then they'll go back down to the reactant level. But let's say they do collide. Well, now they're up here, and they're in this activated complex. Right? So they have the ability then, as the reaction proceeds, to become product. The product energy here is still lower than the reactant energy. This difference in energy, this energy change for this chemical reaction is called that delta H. That's the energy change for the reaction. And again, this difference here is going to be sent out as heat. This is also an exothermic reaction because the energy in the products is lower than the energy of the reactants. And that energy difference then is sent out as heat. But this reaction has a much larger EA. Now, if you wanted to compare and you looked at these two reactions, You might say, which one would be the reaction that you would think would proceed faster, just in general, and at the same temperature? Well, probably reaction A, because this reaction has a low activation energy. And so at the same temperatures between these two, if they're both, let's say, at 100 Celsius, right, the reactants, they're colliding. Well, the reactants in reaction A don't have to collide with as large of an energy. And so at whatever temperature, let's say 100 C, there's going to be a greater number of collisions that collide with that very small amount of energy needed for this thing to react. Whereas the reaction B, right, if it's at the same temperature as reaction A, these guys are going to collide, and they're not going to be able, not very many or not a large percent of them are going to collide with this large activation energy. So that's one way to kind of interpret this reaction energy profile. Let's look on to the next slide. Okay, so this slide is going to show both an exothermic and endothermic typical reaction energy profile. And so at least at first, you just need to know how to read the reaction energy profile. What are these energies showing you, okay? So again, left-hand side, this is a reaction that would be exothermic. Why is it exothermic? Well, because the energy of the products is lower than the energy of the reactants. This difference between the reactant potential energy and the product potential energy, this is your delta H. That is the energy of the chemical reaction. And again, this would be sent out as heat. Well, let's look at the other parts of this. Well, again, this right here represents the energy in the bonds of the reactants. This level right here on the potential energy scale is the energy in the bonds of the products. The difference between the reactant energy level and the peak of the activated complex here, this transition state, that difference there is the activation energy. In an endothermic reaction, okay, here's the reactant potential energy, here's the product potential energy. The difference between these two levels is going to be your delta H, okay? But you can see, though, that in order to go from reactant to product, irrespective of this activated complex, this reaction, you have to add energy to this reaction in order for the products to be formed, okay? And so this is an endothermic reaction. In an endothermic reaction, though, look, you have your reactant level here. And again, just like any endothermic or exothermic reaction, these guys are going to have to collide. These reactants are going to have to collide, and they're going to have to collide to get to the top of this activation energy barrier. And so again, the activation energy is the difference between the reactant energy level, potential energy level, and the potential energy at the top of this activated complex peak. So that would be the activation energy for this reaction. Finally, to wrap this up, let's look at a blank reaction energy profile and see if we can identify the different parts. All right, so A, well, that looks like the potential energy of the reactants, right? This is the energy of the reactants. Let's look at D. Well, D would be the energy of the products. What is B? B is the difference between the energy of the reactants and the peak of the activated complex. So B represents the activation energy. Okay? Again, this would be an exothermic reaction because the energy level of the reactants is greater than the energy level of the products, and this difference here, this difference between these two levels right here, actually this, and it's not marked on this graph, this difference right here, this would be your delta H. What is C, though? C is defined as, it's the energy from the origin up to the top of the activated complex. That is, C is called the energy of the activated complex. In other words, it's the total energy that needs to be present at the top of that activated energy complex peak, okay? So again, A, reactant energy, D, product energy, B, activation energy, The difference between A and D is the energy of the reaction, called the delta H, or delta H reaction, sometimes written delta H RXN. And C is the energy of the activated complex. All right, that's it for these notes, and we'll see you soon, gentlemen.